Come on. Is it time? I guess we'll call it time.
Yeah.
Okay.
Started recording anyways.
Oh, yeah, really? Okay.
Because I forgot last time to.
Okay. So Sergio, if you're there, I wish you were here. A friend from Spain, now living in Cambridge. So last time we were looking at this thing that's called V3 in my textbook with Richard Tweedy, and please don't think I'm just trying to sell a bunch of stuff in a book I wrote, ages ago. This is the only way known to establish existence of a steady-state distribution for Markov chain, and on top of that, obtain pi of f is finite. It's just I didn't invent this. It's just I happened to write a book where we developed this theory. And the main result is that for a unit chain Markov chain, we end up getting a bound on this sort of cost up until we hit a target state. Okay, and this sort of think of f as like a bound on the cost. It's bounded by the Lyapunov function itself plus a constant, which I'll identify for you in a moment. And because of this, I gave you a representation of the steady state probability mass function. And it exists, and the mean of f with respect to pi is finite, and in fact it's less than b times the pi of s, where s is a set. S is a finite set. This function f here is assumed greater or equal to 1, so this means something. If f was 0 everywhere, it would be pretty meaningless. And v is greater or equal to 0 is used as well. Now, what's funny is last lecture, so, a few lectures back, I told you that, I didn't say this, but let me write it down, pi of c, which my notation for this, okay, so pi of c just means a dot product. It's a steady state mean. So I gave you Kak's theorem. All right, f, it's and this is what we got from the law of large numbers. So when I was doing the law of large numbers analysis, I said this must be the steady state distribution. Then last lecture, I realized I blew a few people's minds when I said this is the invariant PMF. All right, so it's a steady state distribution in the law of large numbers. And again, I guess I should have said this, it's also the invariant PMF. And it turns out this implies this. And so maybe I'll give that to you as a homework assignment. So once you have a steady state probability mass function, it must be invariant. And in fact, I've just decided I will give that to you as a very short. Take you 3 minutes to do in the homework. Okay, but I just took this for granted. That's the trouble with teaching a course many times. You forget to mention things. Okay, so the thing is that so this motivated. Well, when are we going to ever know this is finite? And it turns out this is finite if and only if I can find a solution to this equation here, where again, d is just notation for p minus I. Again, that's called V3 in the book. And this, this thing is finite for every x, if and only if we'll see there's a solution to this inequality. And the converse is really nice. It's very simple, but just like in the deterministic theory, it's identical. And so I didn't have time really to give an example last time. Let's do it real quickly. The M1Q is the only reason I use it is it's very simple to work things out. So what you can do instead of, normally you start with f, because after all, f is the bounding function. Basically, there's some cost function you care about, say a quadratic. You're going to take f to be maybe a quadratic plus a constant, something like that. But for the M1Q, let's just start with v and see what f we get. And I think we've basically done this before. But let's just take v of x equals just x to the n and hit it by dv and see what happens. And the trouble is, these examples take so long to do. I fear I'm going to lose the whole lecture, but I'll just see what happens. So what do? I look at dv of x, and what does that mean? It's the expectation of v of x k plus 1 minus v of xk given xk equals x, which is also PV at x minus V of x. And you all are reading this to yourself every night, right? You know this. Okay, and then you just plug the monster in, and let's take x greater equal to 1. So why do I do that? I think I have done this before. It's just this max is really annoying. So this would be a linear recursion except for the annoying max. But given the fact that delta takes on values 1 and minus 1, as soon as x is bigger than or equal to 1, the max disappears. Okay. Did I say n? Yes. Okay, so you can see that's a useful thing to do. All right. And then you go through and you expand this monster out and you get a big mess, right? This is equal to the expectation of the sum k equals 0 to n of, let's see, what's that? N choose k, x to the n minus k, delta 1 to the k, minus x to the n. Is that what it is? So you get a big ugly mess. But you can see the 0th order term gets canceled. And then I've got the n choose 1 term, which is just n. And then I get the rest of it. And I'm just going to write it down. Junk. I'm just writing down just what I just wrote down. Okay. All right, those first terms cancel out, and basically the expectation of delta you go up with probability alpha. So it's a probability of alpha, it's alpha times 1 plus mu times minus 1. I mean, that's just a 1, because there's only 2 possible values. So I write that as minus mu minus alpha, which is negative under the assumptions I always impose, which rho equals alpha over mu is less than 1. So that's called the system load. All right, so you get that. So you get a minus n times mu minus alpha x to the n minus 1. And then what do you do with all this crap? Well, if you really, really care about this problem, you devote a few hours. You either get a bound on this is tight, or numerically get it bound, or something. Compute all the moments of the noise. Which is easy to do in this case, right? Delta takes on only 2 values for each time. The second, what's the second moment of this guy? What's delta squared could take on what values? It could take on 1 or minus 1 squared. so for every even power of delta, you just get a 1, and for odd powers, it's just the same thing. So you could really get nice bounds on this if you wanted to, but what you end up doing in this course is just saying, well, this is just some constant kn times x to the n minus k. N minus 2. And plus 1 maybe. I got to keep that constant term. Are you all with me there? So you've got a polynomial here, and I'm just keeping the largest term. I have to put a giant constant here so I can dominate all the other terms. But you all know that if you have a 4th degree polynomial, if n were 6, I've got a 6th order polynomial. I can bound it by some constant times n to the 6 plus 1. All right? So I don't expect you to do any more algebra than that. Just understand that you can bound polynomials by the highest power, and I throw in that 1 because I do have to worry about if x is 0, for example. And then the only thing left is delta to the nth power. Right? All right, so that's it, right? So I've got dv, I've got a negative thing here, and this thing here, which is killed off by that for large x. Right? And so what are you going to do? You can do something like, I could write this as minus n over 2. Well, I need something else too. Do you all see what I'm doing here? What am I doing here? Well, first of all, I said I want my minus f, I want f to be greater or equal to 1. So on the right-hand side, I want something negative, but not just negative. I want it to be, strictly less than minus 1 for all x. All right? Now, why did I divide by 2? It's a cheap trick to be able to put something negative over on this side. All right? And so now you can see if x is very, very large, x to the n minus 1, forget the constants, is much bigger than x to the n minus 2. So this whole thing is going to be negative outside of a bounded set, a finite set. And so there it is. So that's my f of x. I don't have to write that down. I'll underline it for you. That whole thing is what my f of x is. And again, S is going to be the set in which this thing is positive. you know, so basically when this is positive, that means x is quite small. Because when x is big, that dominates that. Right? You know, y'all see that? Yep.
So does B need to be the final value?
B is some constant, right?
Or like if x goes to infinity?
Yeah, this is gone. Now this is, B disappears then. You see, look at this indicator function of s. So the B only is important for x and s. So it gets annihilated. So B is just some giant constant big enough. And it's, again, you just make sure it's big enough. Again, so this bound holds on the set S. So to try to get tight bounds, so if you really care about getting tight bounds here, then this is like, it'll take us 3 weeks. You know, you have to go through and analyze all these terms and do all this extra work. But if all we want to do is say that this thing is finite, just go through and say, obviously, I can make B big enough so that on the set S, this inequality is satisfied. That's nothing. All I'm saying is that that is finite valued. That is finite valued. And so B is just a bound that's big enough to capture that. Yeah.
So
Yeah.
I guess I can put any portion of the negative part to the...
Yeah, I didn't have to do n over 2. I could have done 9/10, anything I want. Yeah, that's right. It's just a crude way of doing things. It's one of the only tricks I know. 'Cause that's the trouble, is that typically this is what happens. Typically, when you do this, you don't get anything like this form. This form is really cool for analysis, but completely unnatural in terms of what you get when you actually do computations. And so you end up having to take a lot of crude bounds to get in this form. Okay, all right. All right, cool. So I'm going to give you a version of this in the homework to play with. It's almost identical as well. I'm still working the homework. It's not due Thursday, don't worry. Okay. So, but you can see here now, a few comments. So first of all, where did I use the fact that delta took on 2 values? Nowhere. The only thing important I did is I said I stuck to x equal to 1 only because I wanted to throw away the max, right? So it wasn't important at all that delta took on 2 values. And it wasn't even important that it was bounded above. I mean, if delta had taken on arbitrarily large values, that would have been fine. What would have come up is, if delta could be arbitrarily large, then I'd have to worry about the moments, right? And so this like the 10th moment might not be finite, But you see how robust this is. The statistics, I need to know about moments, and if they're finite, and then I get a bound on the steady state mean. Okay. All right, cool. All right, so let's go about and try to get an understanding of why this is true. And any questions first? Yeah. Well, yeah, go ahead.
To recap, so if you have a Markov chain and you can show the box inequality there, then that Markov chain will have an invariant distribution, and the cost function associated with that will be finite.
Yep, right there.
That's kind of like the whole reason why we do this.
Yeah, exactly. But I did. The theorem was stated completely last time, and it's in the representation notes. One thing I didn't say here is that this V3, you also need to assume unichain. So I said clearly last time. So you need the 2 things. You need to verify that irreducibility condition, and then verify that, and you've got that. Okay, cool.
Yeah, then I guess...
Oh, yeah, thank you. Yeah.
I can totally expand, like enlarge the fx to get rid of the mu and alpha, so that this stuff is, at least the bound is incompletely invariant with the delta. Is that right?
Oh, wait. I'm not sure I understand the question. I mean,
if I just like say mu minus alpha is, I just say it's 1. I just would just...
Oh, but you can't. I mean, mu and alpha are given physical properties of the system, and alpha plus mu equals 1. So this is basically given to you. You've got this queuing model. Maybe this came from some control design. And mu and alpha now are fixed, and you're trying to evaluate performance. But what's really important is that, you know, if mu is close to alpha, which means if we're always close to 1, then you're getting a bound in something that's really small.
Yeah, or is I find an upper bound for the last one, for the last line. Upper bound for the f(x).
Well, I'm going to define f to be that. That's my definition of f of x, and it's a polynomial function of x. You know, so this shows that I can bound. I mean, yeah, maybe actually that's right. There's a missing punchline. You know, by the way, I said stick to x equal to 1. Obviously, for x equals 1, I can just deal with that separately. I mean, x equals 0, I can deal with that separately. But no, there's something missing here. Suppose my c of x is equal to x to the n minus 1. You know, that's not less than f. That's less than or equal to the reciprocal of that. You know, and so I would have to go through. I said here, yeah. That's the thing, is that you have to know how to generalize these things. How am I going to deal with a problem when I've got my f doesn't bound my c? What would you all do? Is there any hope? Can anybody see how I could maybe
Discount?
No. I'm not changing the problem. Can I get a solution where this is true? Is my question. I'm not going to change the question. Well, look, it's a linear equation. You know, right here, I can multiply this thing by anything I want. I can multiply through by 100. And so I can actually go through and multiply through by this equation, by this constant. And so I can get this 3 minus x to the n minus 1 instead of having, get rid of this constant. Just by multiplying both sides, by changing v, by scaling v up by a big constant. So really what I'm really saying is that pi of c is less than or equal to, I'm really generalizing this, that if c is less than a constant to my f, then pi of c is less than the same constant times pi of f. So that's a tiny generalization of what I said before. And you get it by scaling both sides. It's changing the layout of a function. If this, if that's 1 over 100, I'll take v and multiply by 100. And then I'll get the equation. So, but here's where you see the issue is that as mu goes to alpha, the cost blows up. So at least you learn that. Anything else? All right. And there's no time in this class, but we don't need S finite. If we're on the real line, for example, or Rn, then S will be compact, and the whole theory extends. So it's not really, I'm sticking to countable state spaces just because I don't expect a big probability background. Okay. All right, so how do you do this? So so we started last time, then I had to stop. Okay, so here I've got this. We had very strict restriction on f that was greater or equal to 1. I have got this thing here that's it's 0 outside of a finite set. let's just look at this inequality and analyze it, right? And it turns out what I'm going to prove to you in the remaining, I hope I can do it, in the remaining half hour, is that theorem and these stopping times tau I'm going to be using are going to be stopping times like a first return time to some set. So basically, if you have that inequality holds, then you have that inequality holds. And the proof requires a little bit of math foundations, which I think are cool to know exists. I'm not expecting you to be, to fall in love with this overnight, but I think that the way in which you prove this result is instructive. So I think it's cool to show you this. And do you see how this looks so familiar? Doesn't it look familiar to you? Do you remember my iteration trick? So when tau was just deterministic, we've proven this already. It was the iteration idea. By induction or pattern recognition, as I said before, this whole thing is just saying that p to the n v plus the sum k equals 0 to n minus 1 of p to the k f is less than or equal to v plus the summation k equals 0 to n minus 1 of p to the k times g. This is a special case. So we did this already. I said I have an inequality, if you have an inequality like this, PV is less than or equal to V minus F plus G, you can hit it by P, hit it by P, hit it by P, and you end up getting something like this. So this is just a generalization to random times. All right? Yeah.
For the power for the P matrix, how come it's not tau?
I said in the special case tau equals n, we get this case. Yeah. Now this is for n not equal to tau. This requires some deep math, which I will tell you without proving. Okay. So I mentioned the starting point. The starting point was this. I define something I'm going to call m sub n. What am I doing? Yeah, oh, that's right. It is correct. So what you do is you basically look at the you take this over the left-hand side. By the way, this might not be finite. All right. So this equality holds even though this might be infinity. So the trick in applying it to this is when g is equal to this turns out to be finite. Okay. I don't think I'll have time to get into that. But with this special form, this sum is always going to be finite for the kind of problems we look at. Yeah. That's too many things to talk about. We'll come back to that next time. So the trick is to go basically and take the thing you're looking at, and notice, as I said before, that if I look at the expectation of n time n plus 1, given the history up to time n, or maybe I shouldn't do that, just so it's still on the board. Yeah, I'll keep the same object. If I take the conditional mean of this given the past, then, and there's a -1 missing. You notice there's a -1 there and a -1 there, so I have to be consistent there. So I take the conditional mean of this given the past. This is already in the past, so it's only this I have to worry about. And then you just go and plug in your bounds, which is right there. This means the conditional, this thing here, PV, is precisely what we have here. That's that's what you're supposed to read before you go to bed every night. So whenever I write a conditional expectation like that, I just mean PV. So this whole thing is less than or equal to that sum minus the first term, last term. Oh. All right, so that's PV. All right. And so I did that last lecture. That's why I'm not copying this. I mean, I skipped a step. That this thing here has a V in it, and it has a minus F in it, and a plus G in it. That's just killing off the last term. And so that's exactly equal to Mn minus 1. And that's what's called the super martingale property. You know, if you have a stochastic process, and when you look at the conditional mean given the past, and that's less than or equal to where you were before, that's a super martingale. So martingale is a beautiful bird, and this is a super one. I think it's, or no, it's not a bird. It's, what is it again? What's a martingale? No, that's a martingale is a thing you put in a horse to keep their snoot heading forward the right way. And this is a super one. It's really, anyway. Yeah, so anyway, so again, like I mentioned, there are big books on martingales. You can get all sorts of pretty results. And I'm just going to give you the very, very simple result we'll be using. So I'm going to impose something absurd, and then I'm going to justify it, you know? And actually, I should say less than equal to tau. So if I've got a super martingale, and it's not going shooting up to minus infinity, so I've got a uniform lower bound, deterministic bound, then I can actually get this. And see, if you have a deterministic time, this is obvious, because you can just iterate this super martingale property. You know, I can take the conditional expectation given 2 steps backwards, and go 2 steps backwards, and get, you know, and I can keep on going down and down and down. We always know the expectation of Mn is less than or equal to the expectation of M0. Sorry. you get that by iterating this inequality, just like you get this by iterating the inequality. It's the same proof. It's identical proof. So we always know that, but we can actually get it with a random quantity subject to some crazy bound like that. But how could you possibly get that? Because I've got this G, there's no conditions at all. G could be huge. And this could, G could be e to the x, and so this is, horrible. So what you do is this. What you do is you you change your stopping time. So first of all, I have a new stopping time here. So this is like a first entrance time. Well, it's not a first entrance time because this is cumulative. I'm looking at sort of like a cumulative cost, and look at the first time it exceeds the value n. All right. Now this is the one in there is just thrown in